Okay, so for the first chapter of the exam, your learning is chapter 11, which are alkenes. So let's first learn about the synthesis of alkenes and how to make them. This is a review of 118A. So let's say we had a halo alkene like this right here. There are two bases that we could use to do the elimination reaction. We could use a small strong base like NaOH or a bulky base like butoxide. So for this elimination reaction, we have two different hydrogens that we could grab. We could either grab this hydrogen or this hydrogen here. For the small base NaOH, which hydrogen do you think the base is going to grab? Yeah, the left one. So the OH minus, so you can grab that one, open up one there, pick out the leaving group, give us the more stable double bond there. And the bulky base, butoxide, since it's so bulky, it won't be able to grab the this hydrogen that would give the more stable double bond because there's more groups around it, giving it so it can only grab the available substituted hydrogen because this. And this elimination mechanism can be tricky because of this anti-periplanar intrusion state. Okay. So let's say we had this ring, and I'm going to draw this as a wedge right there. And let's say NaOH. There's three contenders, three hydrogens that we could grab. And we want to grab the hydrogen that is on the opposite side of the leaving group bromine, which is a dash. So which hydrogen would this NaOH grab to form the more stable double bond? Would it be this hydrogen, or this hydrogen? Yeah, the top one, because would form the more stable double bond because the leaving group and give us this product here. And this methyl group, it was a wedge, but it turned into a planar because this turned from sp3 to sp2, and sp2 carbons are planar, they're flat. Okay. And then I have two practice problems for you guys. We also have and LDA is another type of bulky base like butoxide. So for the first problem here, let's draw in our contending hydrogens, which are the alpha hydrogens. Okay, Stephen, I'm going over the review session for the midterm right now.
Okay, thank you.
Okay. So we have a small, strong base, OH minus, which can grab either of these three hydrogens, and which hydrogen can it grab according to the anti-replanation? This hydrogen here. Yeah, so you know how the anti-replanation is saying that we want the hydrogen on the opposite side of the oh wait a minute, I drew this wrong. Let me draw this.
Yeah, so we could definitely do that and plug it into. That's a way.
So this is our leading group. We want to grab the hydrogens that are next to the leading group.
Sorry.
Yes.
But.
Yeah, so which hydrogen here with the OH grab? This hydrogen here. Yeah, so this hydrogen here would give the more stable double bond, but be careful of the anti-replanation state. This hydrogen is not on the opposite side as the leading group, since they're both wedges, so we can't grab that hydrogen.
We would form the alternate product of the.
Yeah. So we can only grab this hydrogen because this hydrogen is dash, which is opposite side from the leading group from here. Okay. That would give you and this dash C3 remains a dash because it's unreacted, nothing reacted with it.
So now situate the student. You can predict.
Yeah. So this H3 right here is still dash because you see how here this base grab this hydrogen and form the double bond here and kick out that bromine. Nothing happened to this carbon or the CH3. So
That's why you got.
oh yeah, so this is a whole separate problem, and this is a problem by itself. Yeah, and this top one right here is the carbon holding the hydrogen, which is the one that is being reacted with, not this carbon here.
You're saying they are. So then it makes sense, like you're.
Oh, this one right here. Yeah. Yeah, the symmetry goes away because this carbon here was sp3 because it had 4 groups attached to it, but now this carbon here has 3 groups. It's sp2 now, and sp2 carbons are flat and planar. Okay. Does anyone want to try this problem here with the bulky base and E2? Yeah. And why wouldn't it take this hybrid? Yeah. Yeah. Bulky. And this reaction here, the next over is E1 and dehydration. The dehydration reaction with heat, yeah.
That's the only one.
Yeah.
And you'll find that it is one thing that I don't want to get put. Well, the student will leave that.
Yeah. Okay. So now let's go over the dehydration of alcohols, the E1. Yeah. Sounds like we have this. Okay. So we're in acidic conditions here because we have H2SO4, water, and heat. So we're gonna look for an acid-base reaction. Which atom here of the reactant is the most basic atom that will grab the hydrogen? Yeah, the OH hydrogen. So we're going to first protonate the OH hydrogen.
I thought it would be that we're gonna go over here. And then this one coming to and then this.
And we converted this bad leaving group alcohol into a good leaving group water. So since we have a good leaving group, we could just say that that leaving group leaves by itself, forming our compound intermediate. And whenever we form a carbocation intermediate, what do we always look out for? Yeah, rearrangement. So can we rearrange this carbocation into a more stable position somewhere? Yeah. So which position here would the carbocation rearrange? Would this carbon or this carbon? So we're gonna do that. There. And now we have the more stable carbocation that's tertiary. And now here we bring in our nucleophile or base water. Over here, since we have a carbocation intermediate, we can either do a SN1 reaction or E1 reaction. But since we have heat, this heat here will favor E1 reaction, which is elimination reaction and forms a double bond. So we have three contenders to do the acid-base reaction. Which hydrogen here would give us the more stable alkene double bond? Yeah, the left one. So this left hydrogen will get deprotonated from the double bond there. And then we have this one product there. Let's say the heat wasn't there and we do the SN1 reaction. The water would attack the carbocation. And so this E1 would be the major product because of the heat, but if heat wasn't there, then this SN1 product would be the major product.
So it was like so this one is Yeah. Like confused about the benefits.
Now let's go over one more practice one before we move on to the chapter 12 reactions of alkenes. Okay. So can you guys walk me through this reaction? What would be the first step here? Yeah, protonation. And now we converted this bad leaving group alcohol into a good leaving group OH2 plus. And what would happen to this good leaving group OH2 plus? Yeah, it's gonna leave by itself. And what's the next step here? After we have the carbocation intermediate. Yeah, it's gonna be arranged to the more stable tertiary position with the high position. Okay. And then we bring in our water that can act as a base or nucleophile. But in this case, since we're in heat, then we're gonna favor the E1 reaction, which we could grab, let's say, this hydrogen, or this hydrogen over here. Which hydrogen would give you the most stable double bond? Yeah, this isopropyl one right here. Because this double bond here is tetra substituted. It has like 1, 2, 3, 4 groups attached to it, which is tetra double bond. Now let's go over the chapter 12 reactions, which are reactions to alkenes. So chapter 11 was like forming alkenes through E2 or E1 dehydration of alcohols. Chapter 12 is what we could do with those alkenes. So we're going to go over catalytic hydrogenation first. So what this reaction is that it adds H2 or D2 with a metal catalyst. It could either be PDC, PT, or rainy nickel. and it would reduce this alkene and add the hydrogens or Ds on the alkenes. And this is a syn addition where it adds on the same side. So the product here would be or it could also be dashed as well. Now let's go over this one right here. Yeah, so in this case, these two are identical molecules. They're not identical. Oh, actually, yeah, you're right. You will put plus in the enantiomer because this is a class center. This has three different groups. D is different from H. Yeah. So you could put.
So you
Yeah, if it was H2, then you don't have to put anything. But with for in the series, you'll most likely put D2 to show that to test if you know the stereochemistry and if it's a syn addition.
It's different.
Yeah, D2 is different from H2. D2. Yeah, for D2 you have to worry about stereochem.
I was supposed to do that.
So for this one, let's say we are going to add the D as a wedge here and here. If D is a wedge, then what would this isopropyl group have to be? Like what stereochemistry would this isopropyl group be? Yeah, dash. And plus the enantiomer.
I thought this was
And then a year from now, it'll be.
look, I'm not.
Yeah. The same exact thing. Let's say this time we choose dash instead of a wedge for the D dash. So since the D is going to be dash, the other groups are going to be wedges. This is going to be wedge ethyl. This is going to be wedge bromo. And I think that's because you could choose it to be a dash or wedge. It doesn't matter. Just put plus in the enantiomer or draw the other one as well. Yeah. Over. Addition of HX. X could be 3R, Cl, or iodine. So what are the So we're in acidic conditions, which means that we're gonna do acid-base reaction. And think of the carbons that are associated with the double bond are really basic because there's a lot of electrons surrounding them, making them very negatively charged and basic. So we want to form the more stable carbocation. Which carbon here of the alkene will give us the more stable carbocation? Yeah, this one. So that means that the other carbon, the least substituted carbon of the alkene, will grab the hydrogen, pick out the bromine group, and give us the carbocation at the more substituted carbon. Because this most substituted carbon lost the bond, the least substituted carbon still has 4 bonds. And then the Br minus that left from the HBr, since that's negatively charged, that would be our nucleophile. That nucleophile will attract the electrophile carbocation there and give us final product. And the way I drew them as planar for both methyl and bromo, but they're the same thing as bromo could be a wedge, methyl could be a dash, or it could be the other way around, where methyl is a wedge, bromo is a dash. And this is because this carbocation here is on sp2 carbon, and since it's flat, the bromine could attack on the top side, giving you a wedge. The bottom side, giving you a dash on the
It's like you're saying, I will give you $12. Yeah. Yeah. That's like.
Let's go over another example problem. This doing a representation for the Okay, so what would be the first step in this reaction? We're in acidic conditions, so we're gonna do an acid-base reaction. So which carbon here would give us the more stable carbocation? Would it be this carbon or this carbon? Yeah, this carbon. So since we want this carbon to have the carbocation, the least substituted carbon will grab the hydrogen, pick out the chlorine leaving group. And I'm not going to draw in the hydrogen because I'm going to say that hydrogen is invisible. But you notice how here this carbon lost the bond. So that means that it has a positive charge there. And whenever we form the carbocation intermediate, we look out for any rearrangements that we could do. Can we do any rearrangements here? Yeah, which is this side or this side? This side, right? Which we could do a hydride shift. Charge there, and then the Cl minus that left can come in, attack that, and give us our final product. And this means that the Cl could either be a wedge or dash, and the other way around for the here.
So this is our.
Okay, so now let's go over the radical addition of HX, which adds a peroxide like ROOR or H2O2. Right. Oh. And I think on this year's midterm, she's gonna test you a predictive product on this because this is a tricky concept for this reaction. So what this is that, let's say HBr and you have ROOR and E. The important thing here to notice is that we have a peroxide ROR, and whenever I have a peroxide like that, think of anti-Markovnikov product. So you know how in the previous reaction when we add HBr, we added the Br to the more substituted carbon of the alkene. In this case, we're going to add the bromine to the least substituted side of the alkene. Which is which carbon here? Which carbon is the least substituted carbon? This side right here. Yeah. So that's the product there. And I don't know if Mr. will test you on the mechanism of this, but I have the mechanism here. It's like the initiation, propagation, termination step from one in A. Do you guys want to go over that mechanism or just move on to the next one? Move on. Yeah. I don't think she's gonna test out the mechanism. And this right here, the important thing is that only works with HBr. Yeah, that's right. It was the LHI, it would be more substituted. So say you have this. Or it could be, let's say. Yeah, no problem. See ya. So so the Markovnikov product is when the nucleophile halogen in this case adds to the more substituted side of the alkene. The anti-Markovnikov is when it attaches to the least substituted side of the alkene. Yeah. Also, this is being recorded so that I can like send you guys the recording after this is done and the notes, like the notes as well. Yeah, no problem.
But in most
Now let's go over acid catalyzed addition of water.
Anything besides.
So you see how here to the did, but the previous solid we had like alcohol, air, and heat. This was an elimination E1 reaction. Reaction here. So which carbon here would give us the more stable carbocation? Yeah, this one right here. So the other least substituted carbon will grab the hydrogen from the acid. And what do we do from here now? After we form the carbocation intermediate? Yeah, rearrangement, which we see we could do here. And since we're not given heat in the reaction, we're not going to do the E1 reaction. We're going to do the SN1 reaction, where the water is going to attack that carbocation. And then the very last step is to neutralize the positive oxygen and deprotonate the oxygen there.
Yeah, that's it.
Do you guys want to do more reaction or move on to the next reaction? Because like the other ones, I've been like going over the reaction and then doing practice problems, or do you guys prefer going over it once and then going on to the next reaction? On the harder reactions, yeah. So
Like the positive problems.
oh, the practice problems. Okay, yeah. Practice problems. Okay, yeah. Let's go over the practice problems. Yeah. This. So in this problem, this is a little bit trickier because we see that both carbons of the alkene are equally substituted, but we know in the mechanism we do a rearrangement somewhere. So which carbon here would need the carbocation to do a rearrangement step? What the carbocation? This carbon here, the other one is going to grab the hydrogen. And then the rearrangement. So there, carbocation, the more stable for sure. And when you draw the mechanism for this on the test, you notice how here the amplitude was a wedge. It turns it's now sp2 with a positive charge. And then for the water attacks that positive charge. Oh shoot, we got this one's there. with the positive charge on the oxygen. The very last step here is to deprotonate the positive charge oxygen. So we products because this carbocation is flat, so the water can attack on the top side, giving you the wedge alcohol. Attack on the bottom side, giving you a dashed alcohol. Okay, now let's go over the acid catalyzed equilibration of alkenes, which basically converts in between cis and trans alkenes. So let's go over.
Yeah.
So this right here could be any kind of acid. It could be H2SO4, H3PO4, H3O plus, like any kind of like acid. And this is going to be in equilibrium. But which side think is going to be more favored? The product or stable? The trans alkene or the cis alkene? Yeah, so think of steric hindrance. You see how here we have these two groups here? These two groups and here are facing on, meaning that the trans alkene is more stable than the cis alkene. Yeah. Trans is stable. Because cis alkene is both groups can touch each other, steric hindrance. So since this trans alkene is more stable, we're going to have the equilibrium arrow favor the product side and a small arrow towards the reactant side. Okay. Yeah. Yeah, boiling point. Right. And that's because say we had a lot of cis molecules like right here. And you see how here it's like cis. Think of it as like a bucket or a basket. As an excess, it can stack on each other very easily.
Okay.
And if it stacks on each other very easily, more London dispersion forces, like more interactions with each other. But in trans, you see how here like they're staggered around. They're not gonna stack around as much. So this is easier to boil off and temperature. This is harder to boil because they're more close together. Yeah. And that's I think that would be like in a multiple choice question or something. Yeah. So we're to do an acid base reaction. Since these two carbons are equally substituted, we could choose either one to grab the hydrogen and form the carbocation on the other side. And now here we converted this double bond into a single bond. This single bond here can do a re-rotation. Let's say starch. And then what we're gonna do now is that we converted this looking like alkane into a trans looking like alkane. We're going to make the double bond again in this state. And we're gonna use the conjugate base that left from the acid, which is this one. Grab the hydrogen and form double bond there. And on reverse, but mainly towards the transalkene because we want to have the transalkene. Okay, now let's go over a practice on that will be a little bit more tougher than this and more likely on the exam. Can you guys walk me through this problem over here?
So we're gonna go to hydrogen.
Yeah, that's correct. We do a reaction here, hydride shift. And then we bring in our conjugate base and we want to form the most stable double bond that we can. And we have three contenders. We can have this hydrogen, or this hydrogen. This one? Yeah, that's correct. You would grab this hydrogen, form the double bond there. Yeah. Because the other hydrogens would give stable alkene, which is why we chose this hydrogen to form the tetra substituted alkene. We're almost done with chapter 12. We just need like two more. Oxymercuration, demercuration. Oh no, we need like 2, 3, 4. 8. What am I? 9. There's like 10 more. But we're getting to the more difficult reactions now. Yeah, the mechanism. Yeah, we could go over the mechanism as well. Yeah, either oxymercuration, demercuration, or hydroversion oxidation. Yeah, but just like rep it out, like repeat the mechanisms over and over until you have it on like muscle memory for the test. Oxide? Yeah. Yeah.
And I feel like I struggled with a lot of things. Did it help?
Okay. For oxymercuration, demercuration of alkenes, I'm going to go over predict the product and the mechanism. But I don't know if we should go over the mechanism for this because like it's a little complicated. Yeah. It repeats. The one that repeats is hydroversion oxidation. Yeah. And I don't think she would give the hydroversion oxidation mechanism because like since it repeats, you need a lot of space. You need like a whole page for that. Okay. So you know how in other reactions, when we added like H2SO4 and water, we formed a carbocation on the moist substituted carbon, and then we did a rearrangement. Did the alcohol there. But let's say we don't want the alcohol to be at this carbon. We want the alcohol to be here. And that's avoiding rearrangements. We use the oxymerization. And it depends. You could add an alcohol or OR group depending on what you have here. If you have water at the top, you're gonna add an OH. If you have an alcohol or OH, OR group. Now let's go over the mechanism, which is gonna be a long one.
So.
So this is the mercury here. Think of AC as acetate. Two carbon ketone right here. This two carbon carbonyl. Okay. Since mercury is attached to two electronegative oxygen atoms, would mercury be positive charge or negative charge? Yeah, partial positive because oxygen is more electronegative, holding the electrons over to mercury, making it more positive. So that means that this mercury and the mercury is going to kick out this good leaving group at the same time. And then the mercury, as the mercury is getting more electrons from the attack, the alkene is getting less electrons. So the mercury is getting more nucleophilic, the more electrophilic. Yeah, this is all happening all at once. So the alkene is giving mercury more electrons for the mercury to the other group at the same time. And it could either be wedge or dash. I'm gonna choose wedge here. And the reason why this is a good leaving group is because let's say here, this negative charge here. What do you notice by this negative charge? What can it do? Like, can it ground or do resonance or over there? So you see how here this negative charge of the leaving group can like move around these three atoms. Since it's able to move around, it's very stable and group. You don't have to. No, I'm just explaining why this is a good living group.
I'm just gonna inspire me.
Oh, okay, okay.
No, no,
Living
no.
group is-
Because then when I drive.
Oh yeah, yeah. You don't have to draw this. Yeah. Okay. Now we begin our water or alcohol. Let's begin our water. This as like an epoxide, like, and we're in a solution. More substituted side or the less substituted side and acidic. Yeah, more substituted side, and that's because in acidic conditions we want to form the more stable carbocation, which is which carbon here that would give us the more stable carbocation. This one, yeah. So that's why the water will attack that side and kick out the mercury on the other side. And think of this like a SN2 like reaction. Since this water mercury, what the water group be? Dash, yeah. Positive charge. This mercury has positive because it has 3 bonds.
Yeah, right.
Wait, I did it. This is after our first step. The second step, NAB is for reducing agent step. Whenever NAB is for or airline for, think of a hydride ion, which is a hydrogen with a negative charge. And that will just get rid of this whole group here. So, this hydrogen here is going to attack that carbon and kick out that whole group. Next. And then we get this with like Hg liquid O minus oh yeah. I forgot one step here, and I forgot to deprotonate this water. But in mechanism problems, do these in 2 steps. You notice how I deprotonate this water and then the division step. Do it in 2 steps. I combined those 2 steps together. Oh yeah, I can able to do that. But before we do that, I want to deprotonate the water. So let's say and you don't have to draw product here. The mechanism?
Yeah.
Oh, maybe. Hopefully not. Yeah, this should be to predict the product problem. The mechanism we went over it once, but it's like the exact same thing as the one we did last time. Yeah.
Right.
Uh-huh. Yeah. Yeah. So this is HVOAC. The AC is this this people.
Okay, no, I haven't seen the, always.
Yeah, it's the same.
Yeah, my friend.
Yeah, and you guys could predict this.
I literally just like texted you. Oh. This cheese
Okay.
Actually, yeah. Thank you.
The more side.
Yeah. It that way alcohol if we have water. Having this. Yeah, CH3, CH2. Oh, yeah. So it would be an ether instead.
I know.
So with this reaction.
Yeah, this is. I keep seeing that.
I'm gonna circle the. But if we had water instead of alcohol, then this would be OH.
That's like that.
And when you guys like can practice the mechanism for this one afterwards. Yeah.
And I'm thinking this will be on the class. Yeah, so it's yeah, unfortunately, there's like even if we like stand outside of the house, so like we paint the like kind of fun stuff.
Hydroversion oxidation.
Yeah.
Well, no, for the repeating stuff, I'm just gonna say repeat 2 times, repeat 3 times to save like time, you know?
Oh,
Yeah. I don't think she'll go over the mechanism. I don't think she'll tell because it's like too long. Yeah.
Right.
I so we don't do it like a lot. It's so bad. Like I see them. I'm like, you know, we just go, and I can hear it, like in your next step. Things and like, and that is the 15 questions like this. Yeah. I can do it tonight.
So the most important part reaction is the peroxide H2O2 or ROOR because this shows that it's an anti-metallic product. And anti-metallic product shows that it adds an alcohol or the less substance to the side. That one. Yeah, this one. The product is okay, but the mechanism is the long one. Yeah, this one is sin addition, where like you know how you add the alcohol here. If you put this as wedge, then this hydrogen would also be wedge. But since we're all in single bonds, it could do free rotation and then it could be planar. Yeah, it doesn't matter. Yeah.
Can you mind showing an example where it would matter?
Yeah. Wait, what matter? This is the one where it would matter. Yeah. So you know how here, this is R2, like this is just an R group, and this is BG, not BH. BG. And you know how the alcohol and the hydrogen or G, they have to be on the same side. The dash in this case.
Oh,
So first, where would the alcohol be? Would it be at this carbon or this carbon? This one? Yeah. Right. So let's say it's dash. Then what would the stoichiometry for the D be on the other side? It was in addition.
Oh, no.
Dash, yeah. This is when it would matter. I feel like this might be unpredictable. Like I don't know if this is crazy or what. But that's good that you caught that it was where the D and alcohol would be on the same side. In this case, it's both glasses. Okay, how many more for chapter 11 or 12? I mean, 1, 2, 3, 4, 5. Yeah, 5. And 13, 12.
Yeah.
250. Okay. Oh, wait, we didn't even go over the mechanism for this one. Yeah, what's the? Oh my God.
Do you think it's better?
Yeah, skip it. Yeah. I'll send you guys the notes afterwards too. Wait, let me give you guys this really quick. So you know how this is recorded? Yeah, I'll send you guys the yeah, just subscribe to the like the
Thank you.
Mhm. And then you guys can find and how much
Yeah, you did.
yeah, there's the yeah, my personal one. Yeah. Yeah, and then also follow the tutoring one as well.
The same one as this?
Uh, yeah. Yeah. Those on like any questions you guys have, just like DM me on the Instagram there, and then I send it to you. Yeah, no problem. Okay, skip the mechanism or go over the long mechanism. I'll send you guys the notes anyway.
I'm okay.
Skip. Okay. Yeah, I'll send you guys this anyway. Yeah. Okay. Addition of carbene. Oh. Since I work for like the ATC, they don't like encourage private.
Table. We didn't get.
Well, I know some tutors they do their own private tutoring as well too.
Yeah.
I do both. I do group and one-on-one sessions. There's like a flyer there that has like different prices. Yeah. Yeah. The group one is the cheaper one.
My program.
But there's free drop-in over here. HTC. Okay. So this reaction here is making the cyclopropane, which is a three-membered three-membered carbon ring. And this maintains the configuration of the alkene. Like if it was trans, the two groups on the opposite side would still be opposite of each other. So for example, say CH2 and to copper. I'm going to dot these carbons of alkene here as these carbons there. And we make a cyclopropane. You see how here these methyl groups are on the opposite side of each other? This is on the opposite side. It would have to be on the opposite side. This circumference as well. One would have to be a wedge, and the other one would have to be dash. But let's say we had a cis alkane instead. Then we get the same cyclopropane. So what do you think the stereochemistry would be now if we had a cis alkene where the two methyl groups are on the same side of each other?
Would it be coming like up?
Yeah, so these methyl groups are here, or these methyl groups here.
Yeah.
What would the stereochemistry for the methyl groups here? Would they be opposite or the same? Yeah, they could both be dash or they could be wedge. Yeah. And the mechanism for this is really short. So I'm going to draw CH2N2. Looks like this, where the carbon has a negative charge, nitrogen has a positive charge. And think of this N2 as the strongest or like the best leaving group out there that you could have. So that leaving group will just leave by itself because it's able to. And that would give us N2 gas and this carbene over here with and what is funny about this carbon? Like what is it missing? Six electrons, 2, 4, 6. So that means that it's very electron hungry. It wants to grab a bond. So then let's bring in our alkene right here. This alkene here is going to attack that carbon that's electron hungry. And at the same time, when that carbon is getting electrons, it's getting more negative. The alkene is losing electrons, getting more positive. So the carbon will attack the other side of the alkene. And I'm going to flip this upside down where this green carbon here, which means this green carbon. And then these dotted carbons of the alkene are these dotted carbons of the alkene right here. You know that I think it's invisible. And the configuration two groups were and they're still opposite from each other. Let me give you a harder problem that might be on the exam, like supposed to be relatively recent exam.
I thought I.
Yeah. Yeah. I need to do. Yeah.
Yeah, the notes, like the PDF notes, yeah.
Like, what do you want?
Hey Jake.
How good day?
Yeah,
How good weekend?
wait.
How good weekend? How's
Oh yeah, my weekend was good. My weekend was good. How was your weekend? How was it? The test? Oh, not good. Yeah.
I have a question about this one.
Yeah.
Yeah.
That's different. Yeah, that's a different reaction. Instead of making cycles for pain, it makes a cycle for pain with but that was under some reason for some reason. So I didn't go over that in my notes.
Oh, okay.
But I would go over that. Reaction
Oh.
as well.
It's the Kirby reaction.
It's like a lot.
Yeah, yeah. I'm just going over like what's on her. Yeah. Oh,
Yeah, but it's what.
But for.
I guess her coffee grind.
Oh,
No, that's the thing. I don't know if it's like, because I feel like this makes sense when it's just illustration. Okay. I was gonna try. Keep doing
okay. So
I'm still
so we see here, there's an alkene. What else? What other atom is attached to this carbon here? Methyl group are on the same side, and we have this reagent to make the cyclopropane. We're going to make the cyclopropane there, methyl group there, hydrogen there. So it looks kind of weird.
yeah, okay. This is what I was after. Everyone's like, oh, this is-
Oh yeah, yeah. Showing that the methyl and hydrogen are both facing up the same side. The other that you got is this. It looks like
I was. Yeah.
this is the easier way to see it rather than just everything plain there.
It's so. I don't think I'm gonna be able to follow this order. I don't know why. Did he actually? All I want to see.
I'm gonna get water.
On one of the it was why they can simply off the
Okay, Let's try to get this one reaction down before we finish today. It's addition of X2, where X could be BRCl or I. And there's three different cases. There's the CCl4 solvent case, the H2O solvent case, and the RO solvent.
Between that seven, we're gonna have 40 times plus that one, we're gonna have 50. We're gonna have support T times the sine thing. If you were to travel around and get that boundary, that circle. X squared plus Y squared. 49 on this function, this would be what you probably going to do. Now, what do you graphically know that you think about so
Sure.
This right here is going to be anti-addition reaction.
So how do you find critical points of a function of wonder? Like that way, looking at that one, and that point, this is different. Come down to that.
Someplace else to watch it. I just didn't
Well,
watch it.
this is straight up there. So what's your division?
So since this is anti-addition, and we have BR2CCl4, what do you think would happen here in this reaction?
14 does still stay there.
You.
We said that equal to 0.
Oh, no.
Negative 14 doesn't matter, right?
Oh, you're gonna get
Divide that
bromine
out.
acid.
Yeah. And bromines.
What's that negative 0?
And they're anti, so let's say this one is wedge,
0.
the other one would be dash. And since this bromine is dash, this isopropyl group would have to be wedge
I think an angle.
plus dash. If that bromine is dash, then the other bromine would have to be on the opposite side, which is a wedge. And that means that the isopropyl would have to be a dash. There.
So those are points of interest.
Well, you know.
Those
Did
are
we
two
just
places.
put an answer here?
Now let's
Or
compare.
not give
It,
you an
it
answer?
started as a familiar, like,
Have to do the, find the.
Yeah, you could do plus the enantiomer as well, because we have spiral sensor here, spiral sensor there, and enantiomer would be the exact opposite, yeah.
this one, I was.
We can do
It's kind of makes it- yeah, I was like, yeah, I don't even know. I'm like, this is so. easy.
And now we have
So I'm going to draw out the
Up
BR2
in the tree.
like this, where the BR has a single bond to another BR.
0.7, right? 1.7.
So one of the carbons of the alkene is going to attack the
What
bromine,
do you get when it's?
kick out the good living group bromine. And as bromine is getting more electrons, it's getting more nucleophilic. Alkene is losing electron, it's getting more electrophilic. Bromine will come back and attack the other side of the alkene, making this bromonium ion. And this bromonium ion can either be a wedge or a dash. You can choose. Let's say it's a dash.
-7. Let's see, yeah.
I think you want it to be worse.
So if the bromonium ion is a dash, what chemistry would this probably be? A wedge, yeah.
Yeah, I was sitting there and I.
What do you?
said the
Yeah.
wrong answer, and I-
And then the Br minus that left will be the nucleophile, which will attack
I like that.
the most substitute site to give the more stable carbocation, and then kick out the bromine group on the other side, right there. So think of this as like a SN2 reaction, where this is the nucleophile, and this carbon here is the electrophile. And why do you think this carbon here is the electrophile? Why is this partially positive charge?
The -7.
Next up, bromine.
Yeah, it's next to that bromine. So if this there's an SN2 attack, what chemistry would this bromine be attached to this carbon now?
Dash.
So this bromine is attacking this where this is the leaving group. It was a dash. We invert that into
Oh, the back.
a wedge. Yeah, backside attack. That's right. And this is gonna be important for later on when we have H2O or alpha as a solvent.
Yeah, yeah. So then, come down to these two.
And this carbon here has the dash bond to bromine, which still has the dash bond to bromine.
Yeah, for this one, for,
But the bromine now is neutral because
this
the
one,
bond
it's
between that bromine and this carbon broke off
like
and
for
landed on this carbon here. Which is
Yeah.
And you would get this product if you chose a wedged bromonium ion.
Thank you.
Mhm.
Are you gonna, rate this?
Yeah, I will.
Thank you so much.
Yeah, no problem. Good luck on the exam. Okay. And that's the case when we don't have nucleophilic solvent like H2O or water. It gets more complicated when we have water or alcohol. So let's go over that really quick. Yep. Okay, so now this looks very similar to the last reaction, but instead of CCl4 as a solvent, we have water. I'm going to do the same arrows for the mechanism. This carbon is going to attack the bromine, kick out the other bromine. And this bromine being attacked is getting more nucleophilic. It's going to attack the other side of the alkene. And this time, I'm going to make this wet. And that means that this isopropyl would have to be a dash. And this Br minus right here. You know how in the last reaction, we used the Br minus to attract the more substituted side, more substituted carbon. This water here, think of it as excess. Like we have millions more water than Br2. So since we have millions of more water than the Br minus, this
Okay.
H2O nucleophile will take over the Br minus, and the water here will attack the more substituted side. We got the bromonium ion there. And then that gives us
Maybe it's good that she does that.
That's why.
And since this water attacks this carbon and it's SN2, we want to invert the wedge, which would be what? Would it be a wedge or a dash? Yeah, so this water will attack this carbon like SN2 and kick out the leaving group with the wedge. What stereochemistry would the water be if it inverts stereochemistry? Dash, yeah. Because you see how here this was a wedge. We want to invert that into a dash. Right here.
Oh, shoot. No, really, the schedule will be done.
And since that is a dash, we're going to convert this dash isopropyl group into a wedge isopropyl group like that.
It's gonna be completely
As long as like.
solved,
And then
many gaps. in it.
The base Br minus or water can come in and deprotonate the positive charge. That's the last step.
That's what we're going to be doing for the next unit solid here, so. But the one implication though is that the thickness of that, so we have our formula pi radius squared, but the thickness is a small increment of y.
In
And it matters because the radius is the distance from here to this, which was what equation? Y equals. Is that how it looks? But we have to solve it. This needs to be in terms of y, so we can't put ln of x here because it's an 8y integral. Then this needs to be an actual variable. But But that's easy. So what is another name for y equals the delta of x? In other words, we solve for x. An easy way to get rid of an outlet is if you do that. They just. Yeah. So that's what.
And then we have one more case where the solvent is going to be alcohol instead of water.
Similarly, your limits should be in terms of funds. Where does this bottom out? Where's the lowest y value? One. It's just two. Okay, yeah, there. Yeah, and also just keep in mind your.
And this is ROH, where the R in this case is the upper
Those
group.
powers get multiplied. That's
So the
not
exact same thing. Attack that.
We happen to
Got that.
because X axis is the X
Yeah.
Y
And then we have this Br minus nucleophile floating around, but we have the alcohol in excess, like we have it a million times more in amount than the bromine is. We're just going to overpower the bromine and be the nucleophile instead. Attack the more substituted carbon. Take that bromonium ion on the other side of the carbon. This is going to invert stereochemistry. So if this was a dash, what would it be if it's inverted? Wedge, yeah. So it would be a wedge. Alcohol. This oxygen here has the ethyl group with the hydrogen positive. This is gonna be dash isopropyl now. Dash bromine still. And then
No, but
Br minus can come in
it's just really fun.
and
So I think
neutralize the negative, the positive charge of oxygen.
it's what happens here. I think it's another, yeah, I think that's like, it's like really similar. Like that one is one.
And that gives us
Because it's always so similar. And it works on the ring. It's like. It also works with the ring. It's just like. Nothing.
But you notice how here, when we added these groups, like the bromine or the alcohol or water or ether or bromine, they're all on the opposite side. Like this is dash, this is the wedge. That's the anti-addition. And then this is plus and answer. So much. I know. Yeah. My shift ends in like 6 minutes, so let's just do one practice problem on this and then wrap it up. But then you got the notes and everything, right? Yeah. You have lab or class? Oh, you have lab or class? Let's see. Okay, last problem. Last problem here.
Keep going, the next one's like 4.87. So you're starting to get a feeling that what's it gonna convert to the thing. Seems like it's gonna hurt. So, yeah, let's say, probably gonna be like 0.99.
Okay, yeah, you try this one.
More like 99.
Yeah, no problem. See you. You too. Good luck on your exam. Yeah. Yeah, I'll be here tomorrow as well.
But no, like, that's the idea, like,
Yeah, you could try on the board if you want.
Actually,
Oh, you're trying the iPad? Okay, okay.
because I have like my minutes somewhere.
Yeah, yeah, yeah. And then you could double check it. I'll do it her at the same time.
Because I don't really think you know why? I think hard to find out. I know, right? It really helps to copy it.
You got it?
I
Oh, you got it. Yeah, it was good. And they're anti-addiction and also plus enantiomer as well. Yeah.
Oh, you did.
You didn't even draw the mechanism. You did in your head or something.
yeah, it's like,
That's good. That's good.
I'm so tired right now. My goodness.
I know.
Like not from this, but like
Oh,
yeah,
oh yeah, from like the whole day.
yeah.
Yeah.
I don't know how you do it.
I took the class in like 2021, so like I've been reviewing it like over
Yeah.
time as well. But when I first learned it, I was struggling as well. Like
Yeah.
I didn't.
But like how you can like just stand up there and teach for like the entire time.
Oh yeah.
And you're like, I'm just writing notes. I'm not even talking, and then you're like, just keep on going. You're like, wow.
I try to stop and like have you guys like answer to make it more interactive, you know,
Yeah.
like, so it's just not me lecturing and like rambling on.
Yeah.
I want to make sure that you guys understand it at the same time.
Yeah.
Yeah.
I appreciate that.
No problem.
Your shift ends soon? Or
Yeah.
in a minute.
In a minute,
You
yeah.
know who's coming in next?
Let me double check for you.